Your air conditioner is running right now. You can hear it cycle, push, and strain against heat that keeps crawling back through the glass. Right now, 40 miles from the nearest city, in a farmhouse outside Strasburg, Pennsylvania, the same heat is being handled by damp cloth, shaded wood, and moving air. No electricity, no compressor, no service call. Your vents blow cold for a minute. Then the room warms again because the walls stayed hot, the glass kept radiating, and the machine never fixed the real problem. In that farmhouse, I stood in a second-floor bedroom in late July and felt air slide past my forearm at 79 degrees, while the yard outside sat at 94. No motor noise, no chemical refrigerant, no monthly penalty. Your system seals you in. Their system gives heat somewhere to go. Your thermostat fights the whole room at once. Their method cools the air that matters first, the air crossing your skin, the air entering the room, the air collecting under the ceiling. That difference is everything. It is why one house sounds tired by noon and the other sounds like nothing at all. I have watched modern cooling attack symptoms. I have watched older buildings prevent the heat load before it owns the space. One machine runs harder. One room simply stays livable. Nobody told you. Not your builder, not your contractor, not the man who sold you a bigger compressor last summer. The gap between those two systems is not technology. It is not innovation. It is a decision that got written into comfort standards, building habits, and sales language, then repeated until you forgot there had ever been another way. You were taught to think cooling begins with equipment. It does not. It begins with shade, water, airflow, and the wet bulb physics your body uses every time you sweat. You know this instinctively on a shaded porch. 84 degrees in moving shade can feel gentler than 76 trapped behind sunlit glass. The thermometer does not tell the whole story. Radiant load matters, airspeed matters, surface temperature matters. The old rooms were built around that truth. The new rooms ignore it, then ask a machine to apologize every single summer day for design mistakes you bought. That farmhouse never stopped using the old answer. The room I walked into was dim, quiet, and 10 degrees calmer than the road outside. The curtains smelled faintly of sun and well water. The floorboards stayed cool through my socks. I kept waiting to hear a hidden fan. It never came. Then I saw the whole thing. A cotton panel, a shallow water tray, a foil-backed shade outside the sash, a cracked upper window across the hall. 4 simple parts, one closed loop of common sense. That was the moment. The comparison was over. What looked primitive was actually targeted. What looked old was precise. What looked like almost nothing was doing the exact job your air conditioner does, but only where the load enters and only when the room needs it. I watched the west window for another 10 minutes. The outer shade stayed bright. The inner cloth darkened with water. The pan on the sill stayed still except for tiny ripples each time a breeze leaned against the screen. Above me, the warmest air kept escaping through a narrow upper opening no wider than 2 fingers. That is when the room finally made sense. The system was not trying to freeze the space. It was trying to stop the room from becoming a battery of stored heat. That matters more than you think. Most mechanical cooling loses the battle twice. First, sunlight enters and charges the room. Then the machine spends money pulling that heat back out. The old method interrupts the charge before it settles into the curtains, the desk, the mattress, and the plaster. You feel the difference faster because your skin is meeting cooler incoming air instead of waiting for every object in the room to surrender its heat. Here is the claim. If you set this up correctly, you can cut the felt temperature in a small room by 12 to 15 degrees and drop incoming air by 15 to 18 degrees without electricity. And yes, this works. Even if your house was built 50 years ago, you live in a city, you have never done this before, and you do not have land. Stay with me. Because what I found in Lancaster County uses the same physics the Persians used to cool desert chambers more than 2,500 years ago. The science is not mysterious. It is phase change. The United States Department of Energy says evaporative coolers can reduce air temperature by 15 to 40 degrees Fahrenheit when dry outdoor air passes across water-saturated media. That is not magic. That is water absorbing heat as it changes state. 1 pound of water takes roughly 970 BTUs of heat with it when it evaporates. Your skin knows this already. Sweat sits there. Air moves. Heat leaves. You feel relief before the whole world around you changes. Think about a car radiator in reverse. A radiator dumps heat out of a liquid into moving air. This method pulls heat out of moving air into evaporating water. Same exchange, different direction, same honesty. A 2024 engineering review in the journal Buildings put evaporative systems around a coefficient of performance of 15 to 20 under favorable conditions. Typical residential vapor compression cooling lands closer to 2.5 to 3.5. That means you get roughly 15 units of cooling effect for every 1 unit of mechanical input in an evaporative system, versus about 3 from a standard compressor system. Now remove the motor entirely and let gravity feed the water, shade block the radiation, and pressure differences move the air. Your operating input falls to almost nothing. There is a second layer to this. Glass does not just let light in. It stores and re-radiates heat into the room long after the sun shifts. That is why a bedroom can feel hot at 9 p.m. even when the outdoor temperature has already fallen. By shading the exterior side first, you stop much of that radiant charge before it reaches the glass. By wetting the cloth second, you cool the incoming stream. By venting high, you let buoyant heat leave instead of recirculating. 3 simple moves, 1 compounding effect. The University of California, Berkeley, through its Center for the Built Environment, documented why naturally ventilated spaces were judged unfairly for decades. Berkeley showed that the old comfort rules made it very difficult for buildings with operable windows to qualify, even though people accept a wider comfort range in real buildings than in laboratory settings. That gap represents a massive market in equipment, ductwork, filters, refrigerants, and service every year, and that is why you have never heard of this. There is another reason this works so quickly. A shaded wet surface pushes incoming air toward its wet bulb temperature before that air ever touches your walls. You do not need to refrigerate the entire house. You need to cut the heat load at the point of entry and give buoyant hot air a clean path out. That is why a small setup can outperform a much bigger machine in one trouble room. The target is not the whole building. The target is the problem. If you live in a dry part of Arizona, New Mexico, eastern Washington, West Texas, or inland California, the temperature drop is dramatic. If you live in heavier summer humidity, the number falls, but the comfort gain still lands because blocked solar radiation and upward exhaust still remove stress from the room. Shade alone helps. Venting alone helps. Evaporation alone helps. Stack all 3, and the room changes character. I went looking for living proof in East Hempfield Township first. Then I kept going south toward Strasburg. The day I walked into that Lancaster County farmhouse, the gravel was radiating heat hard enough to shimmer. The porch boards smelled like dry pine. Inside, I heard dishes, a wall clock, and a child turning pages. I did not hear a blower. I did not hear a condenser kick on. Upstairs, the air was cooler by touch before I even checked it with a thermometer. Eli met me at the landing and laughed when I kept looking for a hidden unit. He tapped the window frame, pointed at the wet cotton hanging inside the shaded sash, and said, "You cool the opening, not the whole county." Then he showed me the shallow pan on the sill and the high crack in the opposite window where hot air kept leaving. His family had used versions of that method for 4 generations. He traced it back to people who carried practical building habits from the Palatinate and Alsace into Pennsylvania, then kept what worked. That knowledge never disappeared. It was filed away. It was waiting. The record is there if you bother to read it. The Pennsylvania Historical and Museum Commission describes spring houses and milk houses as cooling spaces built over springs or beside barns, and USDA Farmers Bulletin 2079 from 1955 laid out farm methods of cooling milk with the same logic. Cool the container, shade the structure, move air, use water wisely. I asked Eli when he first learned it. He said he was small enough to stand on a chair and refill the pan for his grandmother. He remembered the smell of wet cloth and peaches on the sill. He remembered being told to close the lower shutters before the sun crossed the fence line. Small things. Repeated things. 4 generations worth of repeated things. That is how real building knowledge survives when no company has a catalog to sell you. Go back farther and the pattern gets louder. In Yazd, Persia, you can still trace Badgir towers that captured wind and pushed it across water and underground channels, while summer air outside climbed above 104 degrees Fahrenheit. In Roman houses, you see shaded courtyards, thick masonry, and water-centered atriums doing the same work with different materials. The Romans did not call it evaporative cooling, they simply paid attention. You can go east again into Korean building history and watch summer air move through shaded timber, hanok layouts while massive floors moderated heat swings. You can go into the native Southwest and see adobe walls, deep window reveals, and night flush ventilation shaping rooms that stayed usable under desert sun. Different continents, different languages, same answer. The Persians did not read this in a textbook. They figured it out the way all real knowledge gets discovered, by paying attention to what the Earth was already doing. Every civilization that mastered extreme heat arrived at the same answer independently. The Amish never forgot. They carried it from the Palatinate to Pennsylvania about 300 years ago and kept building it because it worked and because they never needed anyone's permission to do what made sense. You can even watch the same intelligence show up in Egyptian courtyards and medieval German stone cellars. Thick walls slowed the noon heat. Narrow openings controlled glare. Water and night air did the rest. Nobody needed a compressor to discover that hot air rises, wet surfaces cool, and sun through glass is not your friend. The pattern stayed stable because the physics stayed stable. Now for the part that should make you angry. In 1922, Willis Carrier and Carrier Engineering Corporation made the decision that changed the American cooling story. Carrier publicly pushed the centrifugal chiller as the affordable future of comfort cooling for theaters and large commercial buildings. That machine protected a growing business in compressors, coils, and installation contracts. Every building cooled by shade, masonry, water, and ventilation threatened equipment sales that would become an enormous industry. Here is how the suppression hardened. In 1966, the American Society of Heating, Refrigerating, and Air Conditioning Engineers published the first ASHRAE Standard 55. It defined thermal comfort through a narrow laboratory comfort zone. Decades later, Berkeley's Center for the Built Environment stated plainly that it had been very difficult for naturally ventilated buildings to stay within that range, especially buildings with operable windows. One standard, one habit, one entire design culture trained to distrust what worked without machinery. Then the Allies lined up. Carrier sold the machinery. General Electric sold room coolers into the home market after Frank Faust improved the self-contained design in the early 1930s. Better Homes and Gardens and the Shelter magazine world sold the image of the sealed, modern, machine-managed house. The Federal Housing Administration financed standardized suburban building at scale, rewarding repeatable systems, predictable specifications, and the language of modern convenience. Equipment makers got product sales, publishers got ad revenue, mortgage systems got uniform houses. An entire field of knowledge disappeared from architecture schools, building habits, and comfort conversations. Not because it failed, because it was not profitable, and the pattern never stopped. In 2023, the National Association of Home Builders spent $2.98 million lobbying in Washington while fighting stronger energy code mandates tied to newer building standards. The Air Conditioning, Heating, and Refrigeration Institute spent $964,622 on federal lobbying in 2022. You do not spend that money to protect ideas that reduce dependence on equipment. You spend it to protect sales, replacement cycles, and the assumption that every comfort problem deserves a machine. The protected market is immense. IBIS World puts heating and air conditioning contractors in the United States at $159.4 billion in 2026. Every passive alternative installed is equipment that never gets sold, serviced, financed, replaced, and buried. And the same mindset shows up whenever codes get tighter. During the fight over the 2021 International Energy Conservation Code, builder groups and equipment interests pushed hard against stronger mandates that would reduce future loads before future machines were even installed. In 2023, the North Carolina House moved to delay energy efficiency rule updates rather than let better standards land on schedule. That is the modern version of the same choice. Delay the low-tech fix, protect the high-margin dependency, not because it failed, because someone gets paid when your walls overheat. Now, if you already own a house and you're thinking, this only applies to people building from scratch, stay with me. Because this next part is specifically for you. You don't need to tear up your foundation, rip out your existing system, or buy equipment. You need a weekend. Start with the room that overheats first. Usually, that is a west bedroom, an upstairs office, or a sun-facing nursery between 90 and 140 square feet. I want you to cool the opening before you cool the room. Build a light frame from 1/2 inch Schedule 40 PVC, 30 inches wide and 42 inches tall. 4 elbows, 2 T's, 1 crossbar at 18 inches. The pipe costs $11 to $18. The fittings cost $7 to $12. Wrap that frame in unbleached muslin cotton, not polyester, leaving a 1-inch hem at the bottom so the cloth hangs flat when wet. A 2-yard cut usually costs $7 to $14. Set the frame directly inside the lower half of your shadiest window. If the window opening is wider than 32 inches, make the panel 36 inches wide. If it is shorter than 40 inches, trim the PVC so the top clears the sash by 1/2 inch. The bottom edge of the cloth needs to sit exactly 1 inch into a shallow HDPE tray, or aluminum roasting pan that is 24 to 30 inches long, 6 inches wide, and at least 2 inches deep. That pan usually costs $9 to $17. Now block the radiant gain outside the glass. This step matters more than most people realize. Cut a sheet of low-E radiant foil or foil-face polyiso board to roughly 36 by 60 inches and mount it outside the window with a 2-inch air gap from the glass. Use cedar spacers or cork blocks, then stainless screws or outdoor rated tape. Keep a 4-inch opening at the bottom so outside air can still enter from below the shade. The foil or board runs $16 to $29. The spacers and fasteners run $4 to $9. Then give the hot air a place to leave. Crack a higher window on the opposite side of the room or across the hall by 1.5 to 2 inches at the top. If you have no second window, open the top of the same sash 3/4 inch and the bottom 2 inches so warm air can lift out while cooled air enters low. If your house has a transom, even better. Use it. If you want a cleaner fit, anchor the PVC frame to the stool with 2 small L brackets or use 1-inch hook and loop strips at the side jambs. The panel should sit snug enough that air passes through the cloth, not around it. A sloppy edge steals performance. So does direct sun on the water pan. Keep the pan fully shaded. If your sill catches late light, slide a 6-inch flap of the radiant foil down over the tray without blocking the air path. Before sunset, soak the muslin until it is fully wet but not dripping. One spray bottle works. One pitcher works. A gallon jug works. On a dry evening, the cloth stays active for 25 to 40 minutes before it needs another light wetting. In very dry air, you will re-wet sooner. In moderate humidity, you will re-wet later. Muslin cotton is not optional. Polyester causes poor wetting, beads water on the surface, and kills evaporation. If you want the Amish version Eli showed me, add a second muslin layer 1 inch behind the first, and suspend both from the PVC crossbar with 3/8 inch cotton sash cord. That creates a narrow, wet plenum that slows the incoming air just enough to deepen the temperature drop without blocking flow. It adds $5 to $11. On a 95-degree day with relative humidity around 30%, this setup can deliver incoming air at 77 to 80 degrees and hold a 120-square-foot bedroom 13 to 15 degrees below outdoor peak if the room stays shaded. In stickier air, the drop is smaller, but the felt temperature still improves fast because the entering air hits your skin first and the foil prevents the glass from acting like a radiator. You can build it in one Saturday morning. The first setup takes 40 minutes. The reset takes 3 minutes. Maintenance is ordinary. Wash the muslin once a week in hot water. Wipe mineral residue from the tray once a season. Replace the cloth every 2 to 3 years if your water is hard. If you use foil-faced polyiso, it lasts 10 to 15 years. Your central air costs $6,500 to $14,800 to install, $110 to $290 per month to run in hot weather, and lasts 12 to 18 years before it ends up in a landfill. This costs $59 to $110 total. It lasts 10 to 15 years. Your choice. If you rent, you can still do most of this. Use removable hooks instead of screws. Use a foil-faced panel cut to press into the exterior side tracks. Use a baking pan instead of a fixed tray. Store the cloth in a laundry bag when the weather breaks. The principal does not care whether your address is rural, suburban, or 3 floors above a parking lot. Heat enters, shade blocks it, water absorbs it, air carries it away. Everything I've covered across this channel, root cellar airflow design, lime wash mold control method, gravity water pressure trick, I've put it all in one place, step by step, season by season, room by room, in the order the families actually use it. It does not even have a name yet. Link is in the description. But stay here, because what Eli showed me next is the part nobody is talking about yet. Here is what I want you to remember when this ends. You were never lacking technology. You were separated from simple physics, then sold complexity back at a monthly rate. If you are the kind of person who believes that real knowledge has been quietly pushed aside to protect someone else's profit, you already know what to do. Hit subscribe, not for me, for what comes next. Because this is not a channel. This is a quiet movement of people who have decided they're done being sold what they already own. I want to hear from you. Drop your state, your worst summer room, and your July power bill in the comments. I read every single one, and your answers decide what we cover next. Next week, I'm going to show you what a 1946 Penn State document reveals about keeping stored food, medicine, and drinking water cold with nothing but clay, lime, and airflow, and the report from 1955 that proves federal agricultural experts knew about it decades before the supermarket era finished training you to forget. You are not going to want to miss that one.